James Webb just looked at the oldest light in the universe. Right now, while you're watching this, something is happening that almost nobody on Earth knows about. About 1.5 million kilometers away from you, in a place where the temperature sits near 40 Kelvin, a machine is holding perfectly still and collecting light that is older than the sun, older than the Earth, older than almost every atom in your body. It is not a satellite orbiting our planet. It is not a rover. It is not a probe flying toward anything. It cannot be reached. It cannot be repaired. And it was designed and built before most of the galaxies it has now found were known to exist. Before the first exoplanet atmosphere was ever measured. Before anyone had a working number for how fast the universe is pulling itself apart. The light it is collecting left its source roughly 13.5 billion years ago. That is not an estimate someone made up for a headline. That is a measured redshift, confirmed with a spectrograph. And the researchers looking at that data are not using words like interesting, or promising, or as expected. They are using words like too bright, too early, and our models do not allow this. This is the story of the James Webb Space Telescope, and the oldest light it has ever recorded. And here is the part the headlines are not telling you. It is not just what Webb found out there. It is what that light says about the atoms sitting in your bloodstream right now, on this planet, in this room. It is what is happening to the standard model of cosmology in 2026, quietly, in papers most people will never read. And it is what happens when the next telescope launches, on a schedule that is already locked in. Stay with me, because by the time this is over, you will never think about the phrase oldest light the same way again. To understand what Webb is actually doing, you have to go back to 1964, to a field in Holmdel, New Jersey. There was a horn antenna there, a large metal funnel, shaped a little like an old gramophone speaker, built by Bell Labs, to catch radio signals bounced off early communications balloons. By 1964, it was being handed over to two young radio astronomers. Arno Penzias was 31. Robert Wilson was 28. They were given one of the most tedious jobs imaginable: clean up the antenna, characterize the noise, and make it quiet enough to do real radio astronomy. The antenna would not go quiet. There was a faint hiss. It was everywhere. It did not change when they pointed the antenna at a different part of the sky. It did not change with the seasons. It did not change between day and night. If it had been coming from New York City, it would have gotten louder when they pointed at New York. It didn't. They chilled their receiver with liquid helium to rule out heat in their own equipment. The hiss stayed. They checked every joint in the metal. The hiss stayed, and then they found that a pair of pigeons had been nesting inside the horn and had coated the interior in what Penzias later described, very politely, as a white dielectric material. They cleaned it out. They evicted the pigeons. The hiss stayed. That is the mundane detail worth holding on to. Two men in their 20s and 30s, scraping bird droppings out of a metal funnel, annoyed at a noise they could not remove. 40 kilometers away, at Princeton, a team led by Robert Dicke was building a detector specifically to look for a predicted leftover glow from the early universe. Gamow, Alpher, and Herman had predicted something like it back in the late 1940s. Dicke's group had not finished building their instrument yet. A phone call connected the two groups. Dicke hung up and told his team, in one of the most quoted lines in 20th century science, that they had been scooped. The hiss was the cosmic microwave background, the oldest light in the universe. Penzias and Wilson shared the Nobel Prize in Physics in 1978 for a noise they had spent a year trying to delete. Think about the sequence there. The discovery did not come from a telescope pointed at a target. It came from two people trying to make a measurement cleaner. The signal was so uniform, so completely without direction, that it looked like a defect in the hardware. The only reason it was recognized at all is that somebody else, 40 kilometers away, already knew what to expect. That pattern repeats through this entire story. The most important results tend to arrive as problems. From there, the work became refinement. In 1989, NASA launched COBE, and in 1992, the team led by John Mather and George Smoot reported the first map of tiny temperature variations in that background. Differences of about 1 part in 100,000. Those faint ripples are the seeds. Slightly denser regions pulled in more gas. More gas meant more collapse. More collapse eventually meant stars. WMAP launched in 2001 and sharpened the map. Planck launched in 2009 and sharpened it further. And it is Planck's numbers that give the 13.8 billion year age used throughout this video. So by the time the James Webb Space Telescope was seriously being designed, the beginning was already photographed. What was missing was the middle. The gap between a smooth glow at 380,000 years and a sky full of galaxies. Hundreds of millions of years of history that nobody had ever seen. And that is the turning point that matters for this whole story. Because it means the actual oldest light was already found. In 1964. By accident. Before the James Webb Space Telescope existed even as a sketch. So what is Webb looking at? Here is the physics, one step at a time. The universe is about 13.8 billion years old. For its first few 100,000 years, it was hot enough that atoms could not hold together. Electrons flew free. Free electrons scatter light. So the early universe was not transparent. It was fog. Then it cooled. At roughly 380,000 years after the beginning, electrons and protons combined into neutral hydrogen. The fog cleared, and all the light that had been bouncing around suddenly had nowhere to bounce. It just traveled. That light is still traveling. It is still arriving. It is hitting you right now. But it has been stretched. Space itself has expanded for 13.8 billion years, and light stretches with it. What started as a fierce orange glow has been pulled out to a wavelength of about a millimeter. It now sits at roughly 2.7 Kelvin. Microwaves. That is why it is called the cosmic microwave background. Now the important part. The James Webb Space Telescope cannot see it. Webb is an infrared telescope. Its instruments cover a range from around 0.6 of a micron out to about 28 microns. The cosmic microwave background sits far outside that window. Webb is physically incapable of detecting the oldest light in the universe. COBE did that in the 1990s. WMAP refined it. Planck mapped it in extraordinary detail. So when a headline says, Webb looked at the oldest light, that is not what happened. What Webb does is different, and in some ways harder. After the fog cleared, there was a long stretch with no stars at all, just cold, dark hydrogen. Then gravity pulled that hydrogen into knots. The knots collapsed. They heated, and somewhere in the dark, the first stars ignited. Webb hunts for that. The oldest starlight. The first objects that ever produced their own light. And that light has been stretched too. A star's ultraviolet output, redshifted by a factor of 15, does not arrive as ultraviolet. It arrives as infrared, which is exactly why Webb was built to see in infrared, and exactly why it has to be so cold. Because a warm telescope glows in infrared, and would drown out the very thing it is trying to see. That is the whole design argument. That is why the machine sits 1.5 million kilometers away, at 40 Kelvin. Consider what infrared actually is. It is heat. Your body radiates it. A warm mirror radiates it. Room temperature metal glows in the exact band Webb is trying to read. Building an infrared telescope on the ground, or even in low Earth orbit, with a warm planet filling half the sky, is a little like trying to hear a whisper while standing inside a running engine. So the machine had to be moved somewhere it could get cold and stay cold. It sits at the second Lagrange point, a spot on the line running from the Sun through the Earth and outward, where a spacecraft can keep pace with our planet as we orbit. From there, the Sun, the Earth, and the Moon all sit in roughly the same direction. One shield blocks all three at once. Behind that shield, the mirror settles to about 40 Kelvin. That is around -233 Celsius. One instrument, MIRI, goes further, down near 7 Kelvin, using a dedicated cryocooler, because the longer the wavelength you want to read, the colder your detector has to be. 40 Kelvin is not a design flourish. It is the difference between reading the light and being blinded by your own equipment. Building a telescope, that cold, that far away, is close to impossible, and it is worth sitting with why. The primary mirror is 6.5 meters across. That is too wide for any rocket fairing ever built, so it was cut into 18 hexagonal segments, made of beryllium, coated in a layer of gold thinner than a wavelength of the light it reflects, and folded like origami. To stay at 40 Kelvin, it needed shade, not a little shade. A 5-layer sun shield, roughly the size of a tennis court, each layer thinner than a human hair, separated so that heat radiates sideways, out of the gaps, rather than passing through. The sun-facing layer runs hot enough to boil water. The far side sits near 40 Kelvin. That is the whole point of the machine. It launched on Christmas Day 2021 on an Ariane 5 from French Guiana. Then it spent a month unfolding itself, alone, with no one aboard and no possibility of rescue. NASA engineers counted roughly 344 single-point failures in that sequence. A single-point failure means exactly what it sounds like. One component fails, and there is no backup, and the mission is over. Not degraded. Over. Hubble orbits about 540 kilometers up. Astronauts flew to it 5 times. They replaced its gyros. They installed corrective optics after the mirror came out wrong. Webb sits at 1.5 million kilometers. Nobody is going. There is no plan, no vehicle, no procedure. If a mirror segment had jammed, the answer would have been, that is the telescope we have now. The distance shows up in smaller ways too. A command sent from Earth takes about 5 seconds to arrive. The reply takes another 5. There is no real-time steering. You send instructions, and then you wait. There is one more constraint that rarely gets mentioned. The 18 segments do not just have to unfold, they have to be aligned to work as a single 6.5-meter surface. That alignment is measured in nanometers. Each segment sits on actuators that can nudge it in steps far smaller than the width of a virus. Getting 18 separate mirrors to behave as one mirror, remotely, at cryogenic temperature, with a 10-second command round trip, is the part engineers still talk about. Every deployment worked, all 18 segments aligned, the sun shield tensioned, the mirror focused better than the requirement, and then, almost immediately, it started producing results that nobody had a model for. The first result that mattered came fast. In 2024, the JADES survey team confirmed a galaxy called JADES GSZ14-0 at a redshift of 14.32. Confirmed, not guessed. That number came from NIRSpec, Webb's spectrograph, which spreads the light out and finds specific spectral features rather than relying on the color of a smudge. A redshift of 14.32 puts that galaxy roughly 290 million years after the beginning, out of 13.8 billion years total. Here is the scale comparison. If the age of the universe were a single calendar year, that galaxy's light left when the year was about 8 days old. And it should not have looked like that. It is bright. It is intrinsically large, measured at something on the order of 1,600 light-years across. That is not a first flicker. That is a functioning galaxy, with a substantial population of stars already in it. Which raises the problem the field is still working on. It takes time to build a galaxy that size. Gas has to fall in. Stars have to form. There does not appear to be enough time between the fog clearing and 290 million years to do it comfortably. Researchers still cannot fully explain it. Then it got stranger. In 2023, a team led by Ivo Labbé published a paper in Nature describing 6 candidate galaxies that appeared far too massive for how early they were. The press called them universe breakers. The authors were more careful than that, and said clearly that spectroscopic follow-up was needed. Follow-up came. Some of those candidates turned out to be something else entirely. Webb kept finding small, extremely compact, very red objects. Hundreds of them. They got a plain nickname, little red dots. They are unusually common in the early universe, and essentially absent later. Some show the spectral signature of gas moving fast, which points toward a black hole feeding at the center rather than starlight alone. That would mean supermassive black holes existed, and were already large, when the universe was a few 100 million years old. There is no settled model for how you build a black hole that heavy that fast. The standard picture starts with a dying massive star and grows outward over billions of years. That timeline does not fit. Alternative ideas exist: direct collapse of gas clouds, unusually dense star clusters, and none of them are confirmed. This is one of those places where the honest sentence is the short one. Nobody knows yet. Now the part that touches you directly. Every atom in your body, heavier than helium, was made inside a star. The oxygen in the breath you just took, the calcium in your bones, the iron in your blood. None of it existed in the early universe. The early universe was hydrogen, helium, and a trace of lithium. That is the whole periodic table for the first few 100 million years. So the expectation was that the earliest galaxies would be chemically almost blank. They are not. JADES GSZ14-0, that same galaxy at 290 million years, was later observed with ALMA in Chile, and the observation indicated the presence of oxygen. Oxygen, in a galaxy seen when the universe was 2% of its current age. That means stars had already lived, fused heavier elements, died, and returned that material to the gas around them. A full stellar life cycle, completed, inside a window that was supposed to be too narrow for one. Here is the relatable version. Imagine finding a fully stocked kitchen in a house where the foundations were poured last week. The chemistry that eventually built you started earlier than the models allowed, and the models have not caught up. There is a second thing those early galaxies appear to have done, and it involves the fog again. After the universe went transparent at 380,000 years, it did not stay simple. The gas was neutral hydrogen, and neutral hydrogen absorbs ultraviolet light very efficiently. So the young universe went through a stage where starlight could not travel far before being swallowed. Astronomers call the period that follows reionization, the era when something stripped the electrons back off that hydrogen and made space clear again. The question has always been, what did it? Early galaxies, or the growing black holes at their centers, or both? Webb has been able to survey faint, small galaxies in that era, in numbers that were simply not reachable before. And the emerging picture is that there were far more of these small, energetic galaxies than the models predicted, and that they may be leaking enough ultraviolet radiation to do the job on their own. Here is the scale comparison. Not one floodlight clearing the fog. Millions of small torches, all lit at once. It is not settled. The measurements of how much radiation actually escapes a galaxy, rather than being reabsorbed inside it, remain difficult and contested. But the balance of evidence has shifted, and it shifted because of a 6.5-meter mirror sitting at 40 Kelvin. There is one more result, and it is the one that quietly unsettles cosmologists the most. There is a long-running disagreement about how fast the universe is expanding. Measurements taken from the cosmic microwave background, that same 380,000-year-old light, give one value. Measurements taken from nearby objects, by climbing a ladder of distance markers like Cepheid variable stars, give a higher one. The two numbers do not overlap within their error bars. For years, the most comfortable explanation was that the nearby measurements had a flaw. Cepheids sit in crowded star fields. Maybe they were being contaminated by neighboring stars that Hubble could not separate. Webb has sharper infrared resolution. Teams including Adam Rees used it to remeasure those same Cepheids and check that exact possibility. The crowding was not the problem. The measurements held, so the disagreement is still there, and the easy explanation is gone. It may mean something is missing from the standard model of cosmology, something about dark energy, or the early universe, or physics we have not written down. It may still resolve into a subtle systematic error nobody has found. Either way, a machine sitting at 40 Kelvin, 1.5 million kilometers from your front door, has made a problem harder instead of easier. That is what real instruments do. So where does this go? Webb was budgeted for a 5-year science mission with a 10-year goal. The launch was accurate enough that it used less propellant than planned getting to station, which left more in the tanks. Current estimates put the propellant supply at over 20 years. That points toward the 2040s. But propellant is the limit. Webb has to make small burns to hold its position, and it can only push in one direction. It cannot fly back into its own sunshield. So one day, on a schedule that can be calculated well in advance, the last burn happens. Then it drifts. It will not fall. It will not burn up. It will simply stop pointing where we ask it to, and continue orbiting the sun as a cold, silent object roughly 1.5 million kilometers behind the Earth, for a very long time. Longer than the civilization that built it is likely to last in recognizable form. Before that, reinforcements arrive. The Nancy Grace Roman Space Telescope is scheduled for launch no later than May 2027, and possibly earlier. It carries Hubble-class resolution across a field of view roughly 100 times wider. Webb stares at small patches in extraordinary depth. Roman will survey. Together, they cover both ends of the problem. And after Webb goes quiet, the light does not stop. Photons that left those first galaxies 13.5 billion years ago will keep arriving at this exact spot in space, whether or not anything is here to catch them. There is nothing to stop them. There never was. So what does this actually add up to? Webb did not look at the oldest light in the universe. That light was found in 1964 by 2 men cleaning pigeon droppings out of a metal horn in New Jersey, and it is still hissing through every radio receiver on this planet. What Webb did was find the oldest starlight, 290 million years, a galaxy that should not have been that bright, oxygen that should not have been there yet, black holes that should not have had time, and an expansion rate that still refuses to agree with itself. One mirror, 6.5 meters wide. One shield, 5 layers thick. 40 Kelvin, 1.5 million kilometers out, with nobody coming to fix it. It is finding things our models do not allow. That is not a failure of the telescope. That is the telescope working exactly as intended. If you want more of this, real published research, without the exaggeration, subscribe, and turn on notifications so you don't miss the next one.